Welcome to Week 1. This is the first lecture, or Lecture 1A for Week 1, and it'll be covering units of energy. The first thing I'd like to do is talk about energy overview. If we look at the overall energy overview for a building, on the left-hand side we have the actual purchase of energy. Within this, we have individual utility billing that we typically have to look at, and then we look at as historical utility billing, which we're going to be doing later on. On the right-hand side of the screen, we have energy utilization. Normally, this would be divided under 3 categories. We take a look at building envelope, we take a look at all the mechanical equipment, and we take a look at lighting and other electrical. Now, under each of those categories, again, building envelope, mechanical, lighting, and other energy-consuming devices, we have 2 issues that we have to analyze. The first one are consumption issues. A classic example of this are lights on, nobody home. The basic background for this is that I'm using energy that doesn't need to be used. So something is running and it doesn't need to be running. A prime example of this, especially in a normal winter or cold climate, a number of commercial industrial buildings have snowmelt systems. If the snowmelt system is running during the summer months for whatever reason, or it's running when there's no need for snowmelt, this would be considered a consumption issue. The other issue we have to look at are efficiency issues. So in other words, I actually need the device that's running. So in the case of lighting again, I have a class going on, there's students in the class, I need the lights to be operational, or I need lighting to conduct the class, but is there a better way of doing it? So are the lights that I'm using currently the most efficient that I have, or can I use a combination of artificial lighting and natural lighting? Is there a better way of doing it? Can I do the process more efficiently? So again, when I look at energy utilization, I have to look at 2 concerns. Is the process necessary at the moment? That's a consumption issue. If the process is necessary at the moment, am I doing it in the most efficient manner? What we're going to do now is we're going to look at common energy units. It's crucial to understand and know common units of energy. Poor understanding of energy units leads to mistakes in the energy calculations. What this can do is when an energy audit report is written up, if a mistake is made, it can lead to one of 2 bad things happening. If a mistake is made and an energy suggestion comes out low, a customer may not take or do that energy recommendation. If the estimate is made too high, a customer may come through and go, wow, I should do that energy recommendation, and they never receive a return on investment, and they're not likely to use you as an energy consultant anymore because they can't rely on the document that you put together. So what we're going to do is we're going to look at electrical and natural gas energy units. The first one we're going to look at are units of electricity. There's 2 main units of electricity that are used by utility companies. The first one is called kilowatt. It's a unit of electrical power. Now, electrical utility companies use 3 other equivalent terms for kilowatt, and those are power, demand, and capacity. So really, there's 4 terms that are equivalent: kilowatt, power, demand, capacity. If you think of it this way, a utility company must have the generation capacity to meet a customer's demand for power, or kW. Now this is an instantaneous measured unit. In other words, when I turn on any load that has a requirement for power, I have to have that power available at that moment to get the equipment to run. The other unit of electricity is kilowatt hour. That's the amount of power used over a time period, or power times time. If you look at it units-wise, it's kilowatt times the actual hours that the power is used. The utility company also uses 3 other equivalent terms. So kilowatt hour is equivalent to consumption, electrical use, and energy. This is the most common unit of electrical billing. If we look at your own residential electrical bill at home, you'll typically see charges for kilowatt hour. So it's a very common electrical billing type. Let's take a look at an example. I have a classroom that has the following. There's 10 light fixtures in the classroom. Each light fixture has 2 32-watt T8 fluorescent lamps. The lights are on Monday through Friday, 8 a.m. to 6 p.m. for 50 weeks out of the year. They're never on at any time during the weekend. What you need to do is we need to calculate both the demand, or power, that's kW, caused by the lights, and we need to calculate the annual consumption. That would be the kilowatt hours. So, the first thing is calculating demand, or power. So we have 10 fixtures per room, times 2 lamps per fixture, times 32 watts per lamp. This leads to 640 total watts. Now, utility companies don't use the unit watts. They use kilowatts. So to convert watts to kilowatts, we have to take and multiply the 640 watts times 1 kilowatt per 1,000 watts. This gives us a total power, or demand, for power by these lights in the classroom of 0.64 kilowatt. Now, the minute these lights are turned on, they demand 0.64 kilowatt of power instantaneously available. Now, if we look on the consumption side, the lights are on 10 hours a day for 5 days a week for 50 weeks per year. This gives us 2,500 hours per year of operation. If we take that hours of operation and multiply by the power, so in other words, kilowatts times hours, we have 0.64 kilowatts times the 2,500 hours per year will give us 1,600 kilowatt hours per year. This is the electrical use, or the consumption, for these lights over the course of the year. Now let's take a look at natural gas. Natural gas is purchased by volume or by energy content. So the units of volume, if it's purchased by volume, the first one, or the most common unit, is CCF. The final CF stands for cubic feet. The first C stands for the Roman numeral C, which is 100. So CCF is 100 cubic feet. The approximate value, in other words, energy content of this, is 100,000 BTUs. Now, when I say approximate, when we purchase gas by volume, it doesn't necessarily have exactly 100,000 BTUs. Depending on where the gas was taken out of the ground from, varies both above and below 100,000 BTUs. So it's an approximate value. When in doubt, you can use the 100,000 BTUs per CCF for energy calculations. The other common unit of volume for natural gas usage is MCF. So again, the CF stands for cubic feet, and the M is the Roman numeral for 1,000. So MCF stands for 1,000 cubic feet. Now in this, we have approximately equal to 1 million BTUs. Again, for the same reasons. Gas purchased by volume has a tendency to vary in its energy content. The second major way of purchasing energy, at least natural gas, is by its energy content. This is actually the preferred way to purchase it, but it's not as common. The unit of energy, or the unit for natural gas, if purchased by energy content, is called a therm. 1 therm is exactly equal to 100,000 BTUs. So again, in the case of purchasing gas by volume, it's their approximate energy values. When purchasing natural gas by energy content, it's exactly equal to a certain quantity of BTUs. Now, some other energy sources and their BTU content. Electricity is 3.412 BTUs per watt, or 3,412 BTUs per kilowatt or kilowatt hour. They're used interchangeably. Number 1, fuel oil, 135,000 BTUs per gallon. Number 2, fuel oil, 140,000 BTUs per gallon, and so forth, as you see on this table. On the bottom, propane, 95,000 BTUs per gallon. When in doubt, or when you're using an energy audit or doing an energy audit, you should go in and check with the U.S. Department of Energy for their going conversions because they vary over time. This ends Lecture 1A, Units of Energy, and you can proceed when you are ready to Lecture 1B. Thank you.